Hey kids, are you tired of learning grade 11 chemistry content from tutors that play cards in science class, or tutors that outsource learning to an ISU project? You've come to the right place. Today, we're going to be discussing the fun world of acids, bases, and neutralization reactions. Mostly because this was the last topic I could pick. Introducing this guy. No, not him, this guy. His name is Svante Arrhenius, and all the way back in 1884 he made a theory about ions. That when solid crystalline compounds, also known as ionic compounds, dissolve, they dissolve into charged particles which Michael Faraday called ions. No one really cared about this work at the time, so he extended his theory into including this key concept for these new hot compounds called acids and bases. When acids and bases dissolve in solutions, acids produce more hydrogen ions and bases produce more hydroxide ions. Then everybody loved and cared about it. So one of the ways we categorize these simple acids and bases is how they dissolve, or dissociate into simple ions. Strong acids and bases dissociate completely in solutions, while weak acids and bases dissociate only partially. Take a look at this diagram now and try to figure out which acid or base is stronger than the other. I'll wait. So yeah, you'll notice that in these strong acids and bases, there's a lot of dissolved ions, and what's really cool about these ions is that they are electrically charged, meaning these solutions can technically conduct electricity. So we call them electrolytes. Like strong versus weak acids and bases, they're ranked in strength on how many ions are dissolved. Because ionic compounds, strong acids, and strong bases dissociate a ton, they are considered strong electrolytes. On the other hand, weak acids and bases dissociate only partially, so they would be considered weak electrolytes. But then you have these stupid non-electrolytes who just want to be part of the club, but they're really just poser covalent compounds that can dissolve, but they don't really dissociate into ions. Later on in the 1920s, two other guys did some independent studies, Johannes Nikolaus Bronsted and Martin Lowry, and extended this definition of acids and bases to what it is today. Remember how acids increase hydrogen ions in a solution when they dissociate, and bases increase hydroxide ions in a solution when they dissociate? Well, these two blokes found something really interesting with dissolved acids and bases. That's right, acids can be called proton or hydrogen ion donors, while bases can be called proton or hydrogen ion acceptors. This results in something called an acid-base reaction, or a neutralization reaction. Because when an acid and base react together, no matter the strength, the result of the reaction will be a neutral ionic compound, also known as a salt, and water. But why is it called neutralization, you ask? Well, if we were to look at the net ionic equation of a neutralization reaction, we'll see that it's just hydrogen and hydroxide forming water together. Moving on, have you ever been to the dentist and he tells you, you can't drink all that soda and eat all that stuff because the pH level will ruin your teeth? Well, you can thank these two guys for it. In their experiments, they found these really cool properties of acid-base reactions called conjugate bases and conjugate acids. Basically, what you need to know is that neutralization reactions produce these. Conjugate acids are essentially bases, and conjugate bases are essentially acids. They're just formed by the acid donating a proton, also known as a hydrogen ion, to the base, differing only by one H+ ion. Side note, substances like water that can act both as an acid and base, and form conjugate acids or conjugate bases are called amphoteric. So, for example, if you dissolve an acid in water, the properties of the water will have a bit of a neutralization reaction and turn the water a bit acidic and make the acid a bit basic when it donates a proton to the water to form something called a hydronium atom. What is a hydronium ion, you ask? Well, it's something that our good friends Bronsted and Lowry used to come up with a new property called pH. Ions dissolve differently, so we needed a new way to categorize them better to find out how acidic they are. pH just means power of hydrogen, and it's a logarithmic scale measure of the concentration of hydronium ions in an acidic or basic solution, meaning each number from 1 to 14 is a measure of the amount of hydronium ions in a solution produced by the acid or base, and each number after the other would contain 10 times the amount of hydronium ions. You can do the same with hydroxide, but we still really don't use that. It's called power of hydroxide. Obviously, Bronsted and Lowry didn't develop the pH scale. That was our good friend Soren P. Sorensen, who described it in 1907. he defined it as being a solution with a pH of 7 at 25 degrees Celsius being neutral, and a pH less than 7 is acidic, but a pH greater than 7 is basic. Here's a formula for pH. Remember it because you're going to do some calculations with it. Basically, what it means is that using our trusty logarithmic scale, the higher the pH scale, the lower the amount of hydronium ions in the solution. Here's also the power of hydroxide formula. So there's this really super crazy cool proof that Mr. Wilson posted about between the relationship of hydronium ions and hydroxide ions. What this means is that when pH goes up, pOH goes down. So what you could really say is that they're opposites of each other. So to find pH or pOH from one another, you can remember that each scale goes from 1 to 14, and since they're equal to each other, each scale added up would technically equal 14. As well, here's the formula as if you wanted to find the amount of hydronium ions or hydroxide ions from pH or pOH. Try this question here with them. I'll wait. So first, you're going to want to calculate the pOH level from the pH using this formula. pH plus pOH equals 14. Then, you can calculate the hydroxide ion concentration from using the formula OH is equal to 10 to the power of negative pOH. So, a little fun fact, pH is visually measured using an organic dye, which is really a weak acid. It changes color based on the acidity of the solution, letting you know how strong or weak the acid/base is, as well as what the pH approximately is. pH readers use this, unless it's electric, as well as some indicators that you'll probably use for a class experiment. As another side note to the lesson, certain substances that when reacted with acid produce certain products. For example, when a carbonate or bicarbonate reacts with an acid, it produces salt, carbon dioxide, and water. When sulfites react with an acid, they form sulfur dioxide gas, a salt, and water. Anyways, there you have it, the full soliloquy on acid-base reactions. Tune in next week to see me jump into a full vat of acid.